Hello everybody, we're going to do a couple of examples of applications of exponents and logs, but first a quick review. A exponential is a graph or an equation that increases at an increasing rate, so it gets steeper. In the graph to the right you'll see it's green, and as x increases it gets steeper and steeper and steeper. The interesting thing is that if you zoom into it, it keeps maintaining this shape. The log is the inverse, or one way of thinking of the log is the inverse of an exponential reflected around the xy, and that's demonstrated in this diagram to the right. The general form of an exponential is an amount or an individual amount, an amount at a point in time is expressed as A equals A, 0, so the starting quantity, times by a positive constant and some element of time, or t or time, or some other variable. If the b is greater than 1, the model represents growth. So you need to be aware of the number you're multiplying by the original amount. Read the question carefully to identify whether it's growth or decay, and that will give you a fair idea of what number needs to be there. But a growth example might be growth of cells, population growth, or compounding interest. If b is less than 1, the model represents decay, and that means you're multiplying it by a point something, so of course it's going to get smaller and smaller, and that might be radioactive decay or cooling of materials. So the first example we'll go through is a growth example. Now these are not from your textbook, and I think they're harder examples from your textbook, but if you step through it, I think you'll be able to do all the questions in your textbook fairly easily. So what is the generation time of a bacterial population that increases from 5,000 cells to 100,000 cells in 4 hours of growth? It's asking you what period of time does the cell double? Because in biology, cells divide into 2s, they divide into 4, and so on and so on. So we can rewrite the formula. It would be nice if you could remember this, but you'll be able to work it out. The amount at some time in the future, and we're given that, so that's 1,000, 100,000. Oops, where are we? That is 100,000. Oops. 100,000 there, 100,000 there, that's where that comes from. The 5,000 is our initial amount. The time we're given is 4 hours of growth. 4 hours of growth. And the cells divide into 2. So we've identified the information that we're given. So that's the 5,000, 100,000, and 4 hours. And we can plug those into the formula. So we want to know, so we are given that at some point in time we have 100,000 cells. We started with 5,000 cells and it doubles for certain periods of time. The amount of time we're after is 4 hours, and the TD is the generation time. So how long, that's the time it takes for the amount to double. Okay, so if we just look at the left here for the moment, if we just look at this portion here at the moment, we divide throughout by 5,000. That gives us 20 equals 2 raised to. That's not very clear. So that's 2 raised to 4 on TD. And we use our log laws to determine that TD equals 4 log natural 20 over log natural 2 over log natural 20, which equals approximately equals 0.92551 hours. So that, remember, that's in hours. Depending on the question, you might need to find it in minutes, and I think that's approximately 55 minutes. be very aware of the units. Be very aware of units. So units matter. Now, how did we get this? That's a very, very good question. So we just move to the right and look at the blue. What he said, 20 equals 2 raised to 4 over x. Now I've just made it 4 over x. 20 equals 4 over x, and x equals td. I'm just using x because it's clearer to see. So we can use the log laws that's shown there in green to rewrite it as the log, first of all we'll take the log natural of each side, and then we can rewrite that using the log laws shown in green to give us log natural 20 equals 4 over x log natural 2, and then we simplify to x. Now this is just one way of doing it. I'll show you a different method of doing it in the next example. And this, of course, comes from the calculator. That, of course, comes from the calculator. All right, so that's a growth example. Let's have a look at a decay example. And this is a nice one because it's 2 steps. The radioactive materials decay at a constant rate, and one model uses the formula. The amount of material at a time is the initial amount times by a constant raised to a power. Okay? You can deduce this. I'm giving it to you this time, but you can deduce what that formula is from general principles. So we have a question. After 1,000 years, a sample of radium-226 has decayed to 64.7% of its original mass. Find the half-life of radium. Half-life is the amount of time it takes for there to be half the amount of material left. So that's so if you started with a kilo, after a certain period of time you would have 500 grams, and then after the same period of time you would have 250 grams, and so on and so on. The period of time for a half-life remains constant. So from the information we are given that the amount at a period of time is 0.647 of the original amount. So that's 64% of the original amount. And the time we're interested in is 1,000 years. So we plug this into the formula. Just add to the formula. Then we divide through by a on 0, so they disappear. Now, this line here, I've used a slightly different method. I've converted to log 2, and we've used this property. So the 2 has dropped down to become the base. 2k becomes the y, and this goes out the back. This goes out the back. Then you use your basic algebra to solve for k. So that gives you the constant. This method can be used to solve the example above. All right, so we've now got part of the information we need. To find the half-life, we consider that the new amount is half the original amount. Okay, the new amount is half the original amount, and we've said from above, well, I'll highlight this in a different color. Oh, this comes from the equation we were given. Okay, so that's where that's coming from. We're just given that equation. So again, we divide through by A0. We multiply by 2 or divide by 2. Sorry, I'll take that back. We apply, at this point, we apply this property down here again. Okay, and log base 2 1/2 equals, sorry, -1. You can use your calculator to solve that. Then we solve for t, get the equation in terms of t, plug our numbers in, and we get our answer. So the half-life is approximately 15.92 years for radium-226. Now, this example and the notes we posted in your OneNote. If you have questions, please do not hesitate to ask myself or your teacher. Thanks.